Hello students, welcome back to Chemical Kinetics. Here in this module, we are going to study Arrhenius equation. But before you study Arrhenius equation, before we start this module, I want you to remember this slide that we did in one of the previous modules. We had seen that temperature increases the rate of chemical reaction. We had also discussed if temperature increases, the rate of chemical reaction increases. If the rate of chemical reaction increases, then rate constant increases. So just a theoretical glimpse we had seen of the relation between temperature and rate constant. But we did not see the quantifiable relationship, the quantitative relationship between rate constant and temperature. It was just a theoretical discussion that if temperature increases, then rate increases, so rate constant increases. But we did not have a mathematical equation which could justify the same. Well, don't worry, this mathematical equation was given by this genius right behind me, Svante Arrhenius. He gave an equation which today is known as Arrhenius equation, based on which we can get the relation between temperature and rate constant. Now this is that equation. K is equal to A into e raised to minus EA upon RT. The first question that will come to your mind when you see this equation is that how on earth did we derive it? But the answer to that is Svante Arrhenius did not derive this equation. It's not a derived equation. It's an observed equation. He observed hundreds of reactions and he studied the relation between temperature and rate constant, and that's how he observed this relation. So yes, it's not a derived equation, it's just an observed formula. K is equal to A into e raised to minus EA upon RT. But what is important here is to first understand the terms of this equation. So here we go. K, as we all know, is the rate constant. EA is nothing but the energy of activation. We have already studied energy of activation in thermodynamics, and we have also seen a glimpse of energy of activation in one of the previous modules when we were doing effect of catalyst on rate of a reaction. Also remember that R is nothing but the universal gas constant. But the value of this universal gas constant depends on the unit of activation energy. If the energy of activation is taken in joules, then R will be 8.314 joules per mole per Kelvin. If the energy of activation is taken in calories, then R will be 2 calorie per mole per Kelvin. It's approximately 2. The actual value is 1.987. Anyway, now T is nothing but temperature in Kelvin, of course. And then you have something called as A over here. This A is called as Arrhenius factor. It's also called as frequency factor. It is also called as pre-exponential factor. All these three are the names of this value called as A. Now what A essentially does is that it keeps the left side and the right side of the equation equal. There is no physical significance of A as such, but we will discuss more about that when we study collision theory. For now, remember this equation, the Arrhenius equation. It gives you the relation between temperature and rate constant. That's all for this module. In the next module, we will understand the graphical representation of this equation. Till then, take care.